Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use phasor diagrams to analyze an LRC circuit. So what we're going to do here is we're going to assume a standard United States voltage source is hooked to a capacitor, an inductor, and a resistor in series. So the standard US power grid is 120 volt RMS voltage, but if you remember, the RMS voltage and the peak voltage differ by a factor of square root of 2, so that's where I'm getting this 170 volts for the maximum voltage. Right? If it's a 60 hertz source, then the angular frequency is 2 pi times the linear frequency. And go ahead and, if you want to pause this and give her a try, 2 pi times 60, I get 377 rad per second. So the actual sine wave or equation that describes the sine voltage input would be 170 volts sine of 377 t. Right? And again, here's where I got the 377 rad per second from 2 pi times the linear frequency. Now to analyze the circuit, what we're going to look for is the impedance of the circuit, the average current, and the power delivered to the circuit. And we're going to use the phasor diagram to tell us these things. So in order to draw the phasor diagram, we're going to need the impedance of the inductor and the capacitor. I'm sorry, not the impedance, the capacitance of the inductor and the capacitor. So the capacitive reactance, right, X sub C, is equal to 1 over omega C, and that's going to equal, in this problem, 1 over 377 rad per second times our capacitance, which is 500 microfarads. And I get, when I run this, I get 5.3 ohms out of that. The reactance of the inductor, X sub L, that's equal to omega L. That's going to be 377 rad per second times our inductance, which is 40 millihenry in this example. That's 0.04 henries. And when we run that, I get 15.1 ohms. Now right now we can tell something about this circuit. The inductive part of the circuit is going to carry a heavier load than the capacitive part. The resistance is higher. So this is going to be more of an inductive type of circuit. We're going to keep that in mind when we draw our phasor diagram. All right, and that's what we do next. So to draw the phasor diagram, all right, I'm going to start just by drawing the axis here. When I draw phasor diagrams, I always start with the input current, or I'm sorry, the current. I always start with the current phasor. So I'm going to go ahead and draw that in red. So there's my current phasor. And again, remember that the instantaneous current is the projection onto the vertical axis here. So the current's a maximum when this point is here. The current's 0 when this guy's here, and so forth. Now we're going to start drawing voltage phasors. Now I don't have them here. I would go ahead and review. If you're not sure where I'm getting these from, you're going to have to review the phasor diagrams for the resistor and the inductor and capacitor. All right, the voltage phasor for the resistor is in phase. So I'm going to kind of move that over, and I'm going to draw my voltage phasors in blue. And again, there's no link between the length of this vector and the length of the current vector. They're just different beasts. So I'm going to call this V sub R, voltage for the resistor. Remember that the current and voltage are in phase for the resistor. All right. Next, we're going to talk about the capacitor. Now, remember, for the capacitor, the current leads the voltage, or another way to say that is the voltage lags the current. So the voltage phasor for the capacitor is going to be down into this quadrant here. Now I'm not going to worry about relative lengths here just yet. I'm going to call that the voltage for the capacitor. Technically here, when I look at this, the resistance is 20 ohms and the reactance is 5.3 ohms. So the voltage for the resistor should be larger, but I'm not going to worry about relative magnitudes just yet. All right, next, the inductor. Now remember, for the inductor, the current lags the voltage, or another way to say that is the voltage leads the current for the inductor. So in this picture, the inductor's voltage would be something like this. There's my voltage for the inductor. Now, I know this one's going to be larger because the inductor has the much larger resistance across it. And remember, each of these is equal to I times the reactance. Now what I'm going to do is take note that the vector sum of the two points up and left. So what I'm going to do is I'm going to replace this vector with one that's equal to the vector sum of these two. So I'm going to go ahead and do that. We're going to get rid of this. All right. Now that's equal to V sub L minus VC. The important thing to realize. Now what I'm going to do is I'm going to put this over here for the purposes of the vector addition. Easier for me to do this than for you folks, I'm sure. I'm going to just erase that little spot I don't need there. All right. And I move this over there as well. Now remember that it's very important that that vector right there is equal to V sub L minus V sub C. And now we can draw the net voltage vector. Right, is the vector sum of these. And that one is equal to the input voltage. All right, so the angle omega t here, that would be this angle right here, but that's typically not important for our phasor diagram. Here's some sort of angle phi that we'll calculate in a minute. Okay, so now we can go ahead and use Pythagorean theorem here. The input voltage squared is going to equal V sub R squared plus V sub L minus V sub C squared. So the input voltage is going to equal the square root of V sub R squared. Now I'm going to go ahead and do this. V sub R, remember, is equal to IR. V sub L is equal to I x sub L. V sub C is equal to I x sub C. All right, that was an L, and this is a C. Each one of these terms has an I, and then it's the resistance term that goes with it. And by the time you square that, it can come out in front of the radical here. So I'm going to go ahead and just put this I right here, and then this is going to be R squared plus, then this is going to give me x sub L minus x sub C, and that's being squared. So this is the impedance of the circuit right here. And then this is the input voltage. I'm going to go ahead and calculate that impedance. Right, the impedance is going to be the square root of 20 ohms. I'm just going to put 20 squared and put an NCU here, plus x sub L minus x sub C. That's going to be 15.1 minus 5.3 squared. I'm going to go ahead and get a value for that impedance. Oops, give me a minute here. Oops, something went wrong. I'm trying to use a calculator on my phone. It's not working super well. Almost there. Well, I get square root of 496. Now this would be ohm squared under the radical here, and I'm just trying to figure out on my calculator how to square root that. I've got just a little phone calculator I'm dealing with. And I'm not seeing a square root button on it. Got to pause this while I find that button. Okay, I'm back. Sorry about that. So I got 22.3 ohms for that. So the impedance of this circuit, approximately 22.3 ohms. All right. We now have enough information to get our average current here. What we can do is I'm going to take my input voltage. Now I want an RMS current. So what I'm going to do is I'm going to use the RMS voltage here. So this is going to be 120 volts equals I times the impedance of the circuit, which we just calculated to be 22.3 ohms. So IRMS is going to equal that 120 volts divided by 22.3 ohms. I get about 5.38, or let's just say about 5.4 amps. Now we'll write the 5.38, I guess. There's the average current. All right, let's talk about that phase angle right there. The tangent of the angle phi is going to equal this voltage divided by this voltage. Now remember that these have IR terms, like this is going to be I x sub L, this is going to be I x sub B, this is going to be IR. So what I'm going to do is just divide those I's out. So that's going to be x sub L minus x sub C over R, which in this example is going to be 15.1 minus 5.3 over 20. And then we want to take the inverse tangent of that. Give me a moment. I get 26 degrees. Actually, I got 26.1 degrees out of this. All right, so we know the impedance now. We know the RMS current. I'm going to go ahead and calculate the power. So the power, which is current times voltage times cosine of the phase angle here. Now, whenever you do power calculations, you always use RMS values. So that's going to be 5.38 amps times 120 volts times the cosine of 26.1 degrees. Okay, and I get about 580 watts out of this. Or about 0.58 kilowatts. So this circuit would be considered to be an inductive type of circuit because the inductive reactance here is much higher than the capacitive reactance. And talk about, what would a change in frequency do? So let's imagine here for a moment that the frequency shifted. It went from 60 hertz to 80 hertz. And I just want to ask ourselves, do we think that will the power go up, go down, or stay flat, or stay the same? So I kind of want to run through that. If the frequency increases, what's going to happen here is that the capacitive load here is going to drop because this number is going to be higher. So, 1 over something bigger is going to become something smaller. So what's going to happen is if the frequency goes up, this is going to go down. The inductive load will go up because the inductive load is proportional to frequency. In our phasor diagram, what's going to happen then, this difference is going to get larger, increasing this angle. So what's going to happen? Power will go down because, a couple ways to see it. One, let's look at the overall impedance. If the frequency goes up, this difference is going to increase. It's going to give us a higher impedance to the circuit. If the impedance goes up, this current's going to go down. Right? It's going to increase this angle because if the frequency goes up, this vector right here is going to get larger in the picture. This one's not frequency dependent. It's going to stay the same. That angle is going to get larger. And when that angle gets larger, the cosine part also goes down. So increasing the frequency will drop the power output of the circuit. Dropping the frequency will have the opposite effect. It'll increase the power of the circuit. As the frequency drops, this voltage difference is going to shrink, and the input voltage will swing towards the current, and the voltage is becoming closer and closer to in phase with the current. So anyway, I just want to talk a little bit at the end of that about conceptually what would happen when we change the frequency. I hope this example helps demonstrate how to use phasor diagrams to analyze LRC circuits. Have a great day.